Okay, here's an application of the differential. Question is, by how much does the volume of a sphere change if its radius changes from 5 to 5.2? Now, we can actually calculate this. We can do 4/3 pi r cubed for r equals 5, 4/3 pi r cubed for r equals 5.2, and we could subtract the two results. I want to do this as a differential approximation. It's not going to be completely accurate. It's going to be a differential approximation, and we'll see how close the approximation is. So how would we apply a differential? Well, first of all, let's get volume as a function of radius, and that's, again, 4/3 pi r cubed, as you should have memorized by 9th or 10th grade and should have reinforced by at least a couple dozen problems, preferably about 100, that apply this. Not sure that ever happens in our educational system. Yeah, very important, very common formula. Everybody should know from age 14 on. Okay, well, first thing we can calculate is, well, v of 5 equals 4/3 pi times 5 cubed. 5 cubed is 125. You multiply that by 4, you get 600. Divide by 3, you get 200. So that's 200 pi. Okay, now we want to find v of 5.2. Well, what I want to do is I want to calculate the change in v as radius changes from 5 to 5.2 using a differential. So I'm going to say, well, okay, dv equals v prime of r times dr. That's the formula. Now the idea is really pretty simple. The derivative of the volume is the rate at which the volume is changing. So the derivative of the volume as a function of r with respect to r is the rate at which volume changes with respect to r. And if you know what that phrase means, you know that if you multiply that rate of change by the change in r, you're going to get something close to the change in v, assuming that dr is small enough. And we're going to talk a little bit about what that might mean. Okay, well, first of all, v prime of r, well, here's our v. So our dv is, okay, derivative of r cubed is 3r squared, so that's going to be 4 pi r squared, which hopefully you recognize as the formula for the area of a sphere. And since you've had calculus, you should probably understand why the change in volume is equal to the area of the sphere times a small change in r. Okay, at least to a good approximation if change in r is small in proportion to r. Well, okay, we do this. Remember that we have r is 5 units. Okay, so if r is 5 units, and you know, it's actually not a bad idea to put the dv of 5 in there and the dv of 5 in here. And for reasons that I'll make clear, I'm going to just pause for a second and put that in. Okay, now this is very consistent with one of the notations that's standard for the differential. But what we're doing is we're finding the approximation to the change in volume if our original volume is calculated at r equals 5. So that's what the dv of 5 is going to indicate. And of course we know that's what we're doing. But then dv of 5 is going to be v prime of 5, which is going to be 4 pi times 5 squared. So I'm going to change these r's. Well, I'll just write it out this way. It's v prime of 5 times dr. And that's going to be 4 pi times 5 squared times dr. And that's going to, well, 5 squared is 25. 4 times that's 100. So that's 100 pi times dr. Okay, remember 100 pi is the radius of a sphere of radius the surface area of a sphere of radius 5. Okay, now from 5 to 5.2, the change in r is 0.2. So our dV of 5, change of volume based on a sphere of radius 5, is going to be this times 0.2. dr is 0.2, so we have 100 pi times 0.2, which is 20 pi, which is then approximately 63. Okay, so, and of course I used machinery to do this. I didn't want to estimate that in my head like I did over here and messed up. So we calculate V of 5.2. We get approximately 187.5 times pi. Now over here, I multiplied 4 by 125 and somehow got 600, and I should have flagged because it shouldn't have come out an integer multiple of pi, but I didn't. And of course 4 times 125 is 500, so we got 500 thirds pi over here where I had 200 pi. So that's equal to approximately 166.7 pi. And now we see the difference. So our difference is V of 5.2 minus V of 5 equals, well, this minus this, and the difference is 20.8 pi, with some uncertainty in that third significant figure of the coefficient of pi. Okay, so that's pretty close to the 20 pi that we got down here, and my 100 was correct here, it wasn't dependent on this calculation. So so here we got 20 pi, here we got 28 pi. The difference between these two, difference between our actual difference and our approximation is 0.8 pi. Okay, so it's very clear that the difference between our actual and approximate values of the volume is 0.8 pi, which is about 2.5. This comes out pretty close to 500, so 2.5 is about 0.5% of 500, about 0.005 or 5% of 500, and I said 0.5%, I believe, but I didn't write it. 0.5% of the actual volume, so we're off by about 0.5% of the actual volume in this approximation, which means it isn't a great approximation, but it isn't all that far off. The approximation of the difference is within about 5%, actually probably within 4% of the actual difference. Now it's worth understanding why there's a difference between the actual and the approximate, and it comes down to a very simple fact that you have a graph. Your 4/3 pi r cubed graph is just a multiple of an r cubed graph. An r cubed graph is concave upward, as you should understand based on just very basic graphing in middle school, much less high school. Okay, so if we have a point on this graph, then if we just use the rate of change at that point, we're just using the slope at that point. So if this line is tangent to the curve, and I think I did a reasonable job of getting a tangent, then we see that the curve tends to curve away above the tangent, so that our actual change, so here would be our actual value, and here, let's say, would be our approximate value. The approximate value following the straight line, where we're just multiplying this rate of change by the change in r. Okay, the actual is going to be above the approximate. And of course, we didn't know much about this function. We didn't already know what an r cubed graph looks like. We could take a second derivative and conclude that it's going to be concave up. So I can add the comment that v double prime of r equals, well, derivative of v double prime is going to be 8 pi r, and that's positive, and that implies that the graph is concave up, so the differential approximation here is going to be low. Now you can also go back to the comments earlier about the rate at which the rate of change changes. That's exactly what this gives you. It means that the rate of change, which is represented by this slope, is increasing. That's literally what it means for the second derivative to be positive, because the second derivative is the derivative of the first derivative, therefore the rate at which the first derivative is changing. Now hopefully you'll be able to tie all these ideas and at least this one application and all the details into a nice tight little bundle, and if you do, you'll have a very good background for applying the differential. I'm going to do one more application in another video, an application actually to a physics situation, a very rudimentary physics situation.